In this video, we'll apply conservation of energy to analyze throttling processes. So let's look at a steam trap, which we've talked about in the closed feed water heater. A steam trap is a valve that allows condensate to pass while inhibiting vapor to pass. Okay, so vapor and liquid can come together, but only liquid will leave the steam trap. So it's going to cause the pressure to drop in a flow, which is what we wanted to do in that in the closed feed water heater system. And this is really what makes it a throttling device. Throttling devices are going to drop the pressure of the flow. So when you see it depicted on a wire diagram of like a Rankine cycle or such, normally you're going to see it either it'll show the circled X. We have it from 6 to 7 because that's where it was in the closed feed water heater diagram. Or sometimes you'll see it as this almost this hourglass look. That's also for a throttling device. Now here's a depiction of a real-life steam trap. This one is basically the idea of here is it's this little bob right here is designed so when it floats up from liquid, it opens a valve. So liquid and vapor come in here. Eventually, the liquid just starts building, or the vapor starts building, it condensates, becomes liquid. As the liquid fills up the bottom of this steam trap, it starts to lift the bob up with buoyancy, and then it opens a valve up. So once it's lifted high enough, a valve opens up and liquid can go out. If it gets to a point where liquid starts to slow down, where it's starting to get too much vapor, not enough liquid, this little bob will drop and it'll seal off the valve. So only condensate can get past. So let's go ahead and try and analyze this steam trap. So we're going to make some basic assumptions. Some pretty clear ones. This is a one in, one exit system. Comes in through the red line, goes out through the blue. We're going to assume adiabatic, so we're going to say that all the heat is trapped in here. You got to insulate this thing normally pretty sturdy like cast iron to try and hold in that heat. And we're going to say that the change in kinetic and potential energy are negligible. There will be some change, more so in the kinetic than the potential, but we're going to treat it as negligible for these assumptions. Okay, so we apply to first law analysis. And so here's our equation for our first law for our steam trap. If we assume that the kinetic and potential energy are negligible, then we just get the heat transfer rate minus the power is equal to the mass flow times the change in our enthalpies. Well, we said it's adiabatic, and clearly there's no shaft work coming along here. There's nothing rotating around. So both those values can be canceled out. So then we're just left with the right side term must equal 0. Well, the mass flow rate's not going to equal 0, so then that means internally enthalpy 7 minus enthalpy 6 must equal 0. Therefore, enthalpy 7 equals enthalpy 6. Now, if your enthalpies are constant across a process, well, we have a phrase for that. It's a special process called isenthalpic. So ice for keeping it constant, same. Enthalpic for enthalpy. We also denote this with a circled H. So we're going to treat our steam traps and our throttling devices as isenthalpic.